So, as we have seen that the work done by a force which is acting on a particle like this, as we have shown here, is given by the dot product of the force vector with the displacement vector, which can also be written as Fs cos theta. Yes, but we have also learned that this formula is valid only when the force acting on the body is a constant. It does not vary with time or with distance travelled by the body, right. So, today let us see what happens if there is a force which changes with time or with distance. How do we find out the work done in that case? So, here we have the situation where there is this block which is initially at the position S1 and it finally reaches at the position S2, but as it moves under the effect of a force which is acting on it constantly, this force is now not a constant. In fact, it varies as S. As the displacement of the body changes, the force changes. Now, in such cases, what we do is, we take the body, the block, let us say at any general position, which I have taken here at the position S, and knowing the force that acts on this body at this particular position, we consider a very small displacement, let us say ds, that the block undergoes under the effect of this force. Now, what is the significance of considering the displacement to be very small, so small that so that it approaches 0? It is a differential displacement that we are taking. The significance is that in this case, if we try to find out the work done, we can assume that for this small displacement ds, the force did not change appreciably, it remained almost a constant. So, that for finding out the small work done in creating this small displacement ds in the block, we can still use the above formula just by replacing s with ds. So, we get an expression which looks like this then, dw, the small work done in shifting the block by a small displacement ds when the force F was acting on it, will simply be given by the dot product of the force vector at that instant with the displacement vector, where now the displacement vector will be a very small differential displacement ds. And now, since we have got this small work done for this particular displacement, we can say that similarly we can find out the small work done for throughout the displacement S1 to S2, throughout the change in the position. And then the work being scalar, all these small work done can be added up to get the total work done by the force on the particle. So, adding up all the small work done will mathematically be represented as the integral of dw, right. So, the total work done w then can be written as the integral of dw, which then becomes integral of f dot ds, and since the initial position of the block is S1 and the final position is S2, S1 and S2 become the initial or the lower limit and the upper limit of this integral. So, this expression then becomes the most general expression in fact for finding out the work done, because it takes care of even those cases where the force acting on the body is not a constant. In fact, if you remember when we started off with the chapter, we said that we start with very simplistic definitions of work, and then as we move further with complex situations, we will refine this definition. So, this is the most refined formula, this is the most general formula that we have then for work done. In fact, all the previous expressions that we have written for work done are just the special cases of this most general expression. Now, let us understand that work done by a force can also be found by finding out the area under the Fs graph, that is the force versus displacement or position graph. How do we understand this? Now that we have obtained this most general expression for work done, which is integral of f dot ds from initial position to final position S1 to S2, we can just compare this expression with the already known expression for an integral of a function of y, which is a function of x. There is a function y of the variable x. Do we all know that if the graph of y looks like this graph that I have drawn here essentially represents y as a function of x, and if you all know mathematically the area under this graph of y from position x1 to position x2 can mathematically be represented as the integral of y dx from x1 to x2. So, here this shaded region that I have drawn here is essentially the area under the curve that we shall get when we evaluate this integral. Now, if we just compare this expression with the expression that we have for work done, we see that the two are similar, and hence we can conclude that just as the integral of y dx gives us the area under the y-x graph, similarly the integral of f ds gives us the area under the, it gives us the work done, because this is work done. So, we can say that the work done is also given by the area under the fs graph. So, then this is how it comes into picture. We have a graph which is for f versus s, any general graph we can have, and then if we want to find out the work done by the force from position s1 to position s2, all we need to do is find out this area under the graph from the initial to the final position. In fact, if we have a force which varies like this, such that it goes below the displacement line also, so that you have negative f values also, somewhere here you will have some negative f values. In this case, you see that the areas that you calculate here, this area which is above the displacement line will be considered positive, whereas the area computed below the displacement line will be considered negative. And then when you try to find out the total work done by this force from, let us say, the initial position S1 to the final position S3, we can break it into two parts. We can write the work done from S1 to S2 first, and then from S2 to S3, which gives us two areas A1 and A2. Mind you that the net work done in this case will be the difference of the two areas, because the area A2 has to be considered negative. The work done corresponding to this area will be negative. Okay. Let us now look at a few examples corresponding to this. First example says a force F, which is equal to 2 plus 3x, acts on a particle along the x axis. Find the work done by F during the particle's displacement from x is equal to 0 to x is equal to 4 meters. So, the force is given to us, and we see that force now is a function of x. So, it is a variable force. As the position of the particle changes, the force also changes. And since the force is acting along the x axis and the particle is also getting displaced along the x axis, it is moving from x is equal to 0 to x is equal to 4, we understand that force and displacement both are in the same direction. So, that will make it easy for us to calculate the expression for work. So, since the force is variable, we will start with using our basic, the most general expression for work, which will be F dot ds from S1 to S2. Since here all the movement is happening along the x direction and the force is also acting along the x direction, we can simplify this to write it as F dot dx, because the displacement is along the x axis, from the initial position x1 to the final position x2. See that since force is acting along the x axis, when we open up the dot product, we will get f dx into cos of the angle between force and displacement, which will be 0 degrees from x1 to x2. Cos 0 is 1, so this goes away, and now we can substitute all the values and solve the expression. F is given to be 2 plus 3x, and then you have dx from x is equal to 0 to 4. Let us solve this. So, we will have the integral will be 2 dx will become 2x plus 3x dx will become 3x squared by 2, and we can now put the limits from 0 to 4. This will give us 2 times 4 plus 3 by 2 times 4 squared, that is 16. And we can simplify this to get the final answer as 8 plus 24, that will be 32 joules. Let us have one more question to solve. A 1 kg mass moves along the x axis and its position as a function of time is given by x is equal to t cubed by 3. Find the work done by the external force in the first second of its motion. Let's observe a few things. The displacement of the position of the particle as a function of time is given as x is equal to t cubed by 3. It is a function of time. That means as the time changes, the position changes, but see that it is not a linear function, it is a cubic function in fact, which makes us understand that there is an acceleration involved here. In fact, we can find out that acceleration. Since the force is not directly given to us, we have to first differentiate this function twice to get the acceleration, and then from there we will get the force, right. So, how do we get this? We first differentiate it once to get the velocity, which will be dx by dt, which when you solve this, this will become 3t squared by 3 or t squared only. This is the velocity of the body as a function of time. From the velocity function, we can find out the acceleration, which will be another differentiation of velocity function, and this will be 2t. Yes. Now, once we know the acceleration, we can find out the force. Force is nothing but mass into acceleration. Mass is given to be 1 kg and acceleration is 2t. So, we just get 2t newtons as the force. And now, let us go for the work done. Work done, by definition, it is integral of f dx in this case, because once again, since the force is acting along the x direction and the displacement is also along the x direction, we can simply write it like this, which when we substitute the values for will give us f is 2t times dx. Now, we have to integrate it for the first 1 second. So, t is equal to 0 to 1, but if you see here, the integrating factor here is dx. So, we can't integrate t, the function containing t here with respect to x. We can't do that. So, we have to make some mathematical modifications here. What do? We divide dx with dt and we multiply also with dt. So, that this dx by dt can now be written as v, the velocity. And we know velocity as a function of time already. So, we can substitute that here. So, see what we get here is integral of 2t into v, which is t squared, into, now we have the integrating factor as t itself, which we can easily integrate, knowing the limits from t is equal to 0 to 1. For the first 1 second we are supposed to calculate it, and now it is simple. We just take the 2 outside and it is integral of t cubed dt from 0 to 1, integrate 2 times t raised to the power 4 by 4, limits from 0 to 1, and this leaves us with 1 by 2 or 0.5 joules.